Now we will have an introduction to derivatives, and derivatives is usually the topic, or the main topic of first semester college calculus, derivatives and their applications. And we'll start off with a simple example. We'll talk about position and velocity in the case of one-dimensional motion. Now by one-dimensional motion we just mean motion along a line. So a good example that we're all familiar with would be a car driving along a road. You could think of a car on a straight road as moving in one dimension. It can either move forward or back. So we have two directions, and we can call one direction positive and one direction negative, and those would correspond to what we normally think of as positive and negative on the number line. And the car's position at any time could be given with a simple number. And that's what the x-axis is used for. And when you drive a car down a road, you don't typically have an x-axis marked out there on the road, but you could imagine one. You could imagine 0 being your starting point, and then at any moment you have a certain position as a certain number of meters or feet or miles along the road. Now if the car is moving, that means the position is changing. And if the position changes over time, and that's often the case, obviously things move in the real world, if the position is changing over time, we can make a graph of position versus time. So let's look at a specific example. Let's suppose a car moved along a road in this fashion, and this line here represents a graph of the position versus time, and it tells you where the car was at any time. So at this time, for example, at 4 seconds, and time here is measured in seconds along this axis, at 4 seconds, that corresponds to this point on the graph. The car was at a position of 20 meters, and this graph shows where it was at any time. Now we know that it started at 0. We see this point down here, and over the course of 8 seconds it went up to a position of 40 meters. Now this doesn't mean that the car went up into the air at an angle. This just means it moved horizontally to the right along the number line that we were looking at just a minute ago, and it moved in a way such that it was at these positions at different times. Now we can calculate the average velocity of the car. Based on the information shown on the graph. Average velocity, by definition, is distance over time. And in this case, that comes out to 40 meters in 8 seconds. And 40 divided by 8 is 5, and note the units. The 40 over 8 reduces to the 5, and we still have meters in the numerator and seconds in the denominator. So this is 5 meters per second, and that should make sense that meters per second is a speed. It goes 5 meters per second, and that's the average velocity. Now we can also calculate the slope of this line mathematically. Remember mathematically that slope is always rise over run. And you might think, well, slope is always delta y over delta x. And that might be true if you have an x and a y axis, like you often do in math class. But we don't have an x and a y axis here. We have a t axis and an x axis. So more generally, think of the slope as rise over run, not y over x, because we don't have y and x here. We have x and t. So the rise here is going to be the change in x. And the run is going to be the change in t. So we have delta x over delta t. And you can see that the change in x is 40 meters, and that change in x of 40 meters corresponds to this time interval of 8 seconds. So 40 meters over 8 seconds gives us 5 meters per second. And it's worth noting that these are the same. And we don't just happen to have the same answer. We have the exact same calculation in each case. Calculating the slope is the same thing as calculating the average velocity. And we conclude this, and you can write this in your notes. We conclude the slope of an x versus t graph is the velocity. The slope of an x versus t graph is the velocity, and by x versus t we mean position versus time, as we see here in this graph. And that's a very important concept, that the slope of a position versus time graph is the velocity. Now let's look at some specific examples. Look at these cases. What if we had a position versus time graph that looked like this? Or one that looked like this? And that's supposed to be a straight line in each case. What's the difference in those two? Well, you can see in the first one that over a fairly long time, there's not a whole lot of change in position compared to the second one. In the second one, over the same amount of time, there's much more change in position. So it goes more meters in a given second in this case. So we could say this first one corresponded to slow movement and the second one corresponded to fast movement, at least slow and fast compared to each other. Okay, let's look at a couple of others here. What if I had a graph that did this? What would that be? Well, you should be able to see that as time goes on, and time always goes forward, so as time goes on, at one time the object was at one position, and then at a later time the position was a lesser number. So that means on our number line the object had one position at one time, and then at a later time it had another position. The object is moving backwards. Okay, this graph does not mean the object is moving downhill. This means that as time goes on, the position decreases in value, so it's moving to the left, or moving specifically in the negative direction. And that's typically what we would call moving backward. The car is in reverse, basically. This is moving backward or in the negative direction. And if we had a graph like this, okay, same thing, it's moving backwards, but this line is steeper in this case. So we would say it's moving backward faster, or at least faster compared to the first graph. Okay, a couple more examples here. Suppose we had an x versus t graph, position versus time, that looked like this. Okay, what does this mean? We've got this smooth curve sloping up, and you can pretend like that's a parabola, even if I can't draw it perfectly. What does this mean? Well, remember we said that the slope of the xt graph, and that's what this is, the slope of this graph is the velocity. So here in the early times you can see it's not very steep, and then as time goes on it's getting steeper and steeper. That means as time goes on the velocity is getting larger and larger. The slope is the velocity. So if the slope is increasing over time, that means the velocity is increasing over time. This object is accelerating. And let's look at one more case. There are plenty of others we could do, and we'll put some numbers on these in just a minute. But suppose we have one like this. Okay, something like that. What does that mean? Well, again, remember that the slope of the graph is the velocity. So there's a large slope at the beginning. That means it's moving fast. And then as time goes on, the slope gets smaller and smaller, which means it's slowing down. And if in fact the slope goes to 0 here at the end, then that means the object is stopped. So we'll say this graph represents an object slowing to a stop.